Hi there, everyone. This is my second try at recording this lesson. I got through it all the way, and then it didn't record for some reason. Super strange. So we're going to try doing it again quickly so that you can get it in time for class. Let's take a look. So we're going to be talking about types of transformations of functions today. We've been looking at reflections and stretches, and those are I'll show you some examples, and vertical translations and horizontal translations. These transformations are going to come from the values a, h, and k with our quadratic functions. So let's take a look in Desmos at what these look like. So over here in Desmos, I have a Desmos here that has some quadratic functions. And here we see y equals x squared. And that's what we would call our parent function, or our basic function. And then if we look at things like, well, if I have an a multiplying that x squared, I put in a slider. So now this a is a number and it can change. As a gets big, we notice that it's going to stretch the values up. So if I take a look at like a stretch of 5, and then let's take a look at values like x equals 2 or x equals 1. All right, here it was down there at 1, 1. Now it's up there at 5. And we'll find that that's true for every value. Like if I go along, this value here, 1.5, well, up there, it's 1.5, 2.25. We multiplied 2.25 by 5 to get up there. So every point has been stretched by this factor here. And those are vertical stretches when a is big. If a is small, like between 0 and 1, we'll get compressions. So here's a half. Okay. Now let's take a look at something like x is equal to 3. And here, the point on x squared was at 3, 9. This point here on y is equal to 1/2 x squared is down there at 4.5. So we call that a vertical compression. Every point has been deformed towards the x-axis. We can also create reflections with a when a is negative. So here's a is negative 1, and basically it's exactly the same as x squared, except the x-axis is acting like a mirror, showing me this function like reflected down. And we can think of that as like a parabola opening downwards instead of a parabola opening upwards. So these are reflections that we're getting and vertical stretches as well. All right, so those are vertical stretches and reflections. Let's keep going. Now, we also want to take a look at vertical translations and horizontal translations. Vertical translations come from this number k, when we're basically adding on directly to the output, and then horizontal translations come from h. Let's look at k first, because it's intuitive. So here we go. If I have another one here like x squared, and then I'm going to add on some number like, let's say 3. Okay, over the slider. All right, so when I added on 3, every point just got lifted up by 3. So if I go along here, say to the point, like I'm going to look at like x values equal 1. This point used to be at 1, 1. Now it's up at 1, 4. Okay, if I change that to 2, this point used to be at 4. Now it's at 7. Every point got lifted by 3. Okay, so that we call that a vertical translation by 3. The shape did not change, but every point changed its position upwards by that amount. If we had here minus 3, oops, I'm going to do minus 33. There's minus 3. Okay, every point went down by 3. So this point used to be at 4. Now it's at 1. All right, so vertically translated downwards by 3 units. All right, so that pretty much is pretty intuitive. It does what you'd expect. If I subtract a big number, it will go down way far. That's minus 100, that's minus 10, that's minus 1. Okay, so however much I take away is how much every point moves down. But what if we looked at horizontal translations? Well, we need some brackets for that. So let's put this one into brackets. And then let's start by adding on 3. 3. Okay, I'm going to turn that off. All right, so now, when I added to the input, when I added directly to the x, I'm noticing that this point 0, 0 now moved over here to the point negative 3, 0. Okay, it slid in the negative direction. Isn't that weird? Because this is positive. Well, you just want to remember that this one is a little counterintuitive. Let's see what happens if we go minus 3. Okay, well, it slid the opposite direction. So negative numbers in there slide things in the positive direction. Positive numbers slide them in the negative direction. So we would describe this parabola as being translated 3 units to the right. Every point moves 3 units to the right. So if I look at like these points at y is equal to 4. Okay. Over here, this point was at negative 2, 4, but over here it's at 1, 4. You see it's moved over by 3. And this point was at 2, 4, and this one over here is at 5, 4, moved over by 3. Every point along the parabola. Nothing changed shape. It only shifted. Okay, so these are horizontal and vertical translations. So one type of question you might have is describing the transformations to some function of x that equals x squared that will produce the function g of x equals negative 3 x plus 5 squared minus 8. So what I would do, and we always start with our a values first. We start with our reflections and our stretches. So I would say this has been reflected in the x-axis and stretched by factor 3. And then it was translated 5 units in the negative direction, 5 units to the left, and then translated 8 units downwards. So let's graph it and see what that looks like. Okay, I'm going to get rid of this one. And this one, we're just looking at the parent function there. And another one, negative 3 bracket x plus 5 and bracket squared. See, it's been reflected in the y-axis, been stretched by 3, been shifted over by 5, and then it was lowered by 8. So there's the new function there. Notice it's narrower because it's been stretched in the y-axis. It's flipped downwards because of the negative a, and the vertex has been moved 5 units to the left and 8 down. So we want to be able to describe these as a series of transformations to the base function. That's going to be really useful, a really useful idea for a lot of other things. How is it useful, Mr. Jennings? Well, let's say that I want to model a roller coaster like this, okay? And let me just pause and sort of erase some of my other work. So if I knew like the equation that modeled this parabola, this parabolic roller coaster, I could then use the mathematics of that parabola to analyze the roller coaster and find out more about it. And let's do exactly that. So one thing that I can do here is I chose to put the vertex there at 0, 0. We're going to see that makes the math a little simpler in this case. And I found one other point that was on the parabola, the point 2, negative 1. So what I'm going to do is copy out my diagram here. And so there is my diagram of the parabola. And I know that this point is 2, negative 1. And that also we have the vertex there, 0, 0. Okay. So I want to find the equation of this parabola. So I know that it's going to be something like y is equal to a multiplied by x minus h squared plus k. But because we chose h and k to be 0, then this is just going to look like y is equal to a x squared. And all I need to do is find that a value. All right, let's take a look. So we want to know how much has it been stretched or compressed so that it goes through that point 2, negative 1. Now, 2 ways we could find this. One is just using technology. So I put the picture in here into Desmos, and then I put in like a y equals a multiplied by x squared. I put in a slider for a, and then I see, well, I definitely want a negative value, don't I? Oh, negative 0.2 is really close. Oh, negative 0.3 is a little too far, right? This is a little too far. Let's try negative 0.25. There, that looks like pretty good, eh? So that's doing it with technology. Let's do it with algebra now. And then we'll compare our results. Okay, so with algebra, what I'm going to do is take advantage of the fact that I know one other point besides the vertex. So this is telling me that there is a point xy on this parabola such that when x is 2, y is negative 1. So I'm going to substitute these values into this parabola. So when y is negative 1, I know that x is 2. All right? So let's do the algebra. So I want to find a, so I want to get that 2 squared away from it. Let's figure out what it is. 2 squared is 4. So I have negative 1 equals 4 4 multiplied by a. And then I know that if I have 4 times a number equals -1, I can find that number by dividing both sides of the equation by the number I'm multiplying by. Division is the opposite of multiplication, so this is what I will do. And then these 4's will cancel, because 4 divided by 4 is 1. So I'm only left with 1a on that side of the equation. So a is equal to -1/4. And there we go. So then I would have a statement here that looks like, therefore, the equation that models this parabola is y is equal to -1/4 a, sorry, not a, oh my goodness, y is equal to -1/4 x squared. And let's check Desmos. So -0.25, that is indeed -1/4. So there it is. It goes through this point, it bullseyes it, and it models pretty effectively the different points along the path of this parabola. Okay? But you might not always be putting the vertex at 0, 0. Here I wanted to have the height of the basketball net at 10, so that my scale matches, like, the reality here. So this is at the point 10, 18. And I want to know, will this ball, if it continues on this trajectory, go through the point 10, 18? Will it go through the hoop and score a three-pointer? So I'm guessing that it was released at 0, 8, and that its vertex is about 9, 15. All right, so let's work with those two numbers and see if we can find the equation of this parabola. Let's go. So I know that my vertex is 9, 15. And actually, let me do this and do this so that we can see all this stuff. Okay, here we go. So, wait, where is it? There it is. Okay, wait, what? Yeah, so the vertex HK is at 915. So I'm going to be inputting that number into, for H and K. Remember that H is a sign flipper, so I have to have -9 in there, x minus 9 squared plus 15. This one's not a sign flipper, so I put that one in directly. So I just substitute in those values for x and y because I know h and k. And now all that I'm left to do is find a. I'm going to use this extra point. I always need one other point. So I chose the point 0, 8 to work with. So that's telling me that when x is 0, when I substitute 0 into this function, I want it to output 8. And let's see how that's going. All right. So, youch. Okay, so 8, the function should be equal to 8 when x is 0. So we're going to have some a, and that's the variable we're going to solve for. 0 minus 9 squared plus 15. Okay, I just take this function here. It's still missing an a value, but when I have that y value there, I'm going to be able to solve for it, that x and y. So let's go ahead and solve for this a. Okay, so first thing that we can do is subtract 15 from both sides to remove that term and move it to the other side. 8 minus 15 happens to be -7. And that's going to be equal to a times 0 minus 9 squared. So that's going to be a multiplied by -9 squared. All right, so it's getting simpler. We're getting a alone. And then let's do another line. -7 is equal to -9 squared is positive 81. So 81 multiplied by a. Now, same idea. I'm just going to divide this 81 away from both sides. All right. And then this 81 cancels that 81. And I found a. -7 over 81 equals a. All right. So the function that's going to show the trajectory of this basketball, according to my points, is something that looks like f of x is equal to -7 over 81 x minus 9 squared plus 15. Oops. Plus 15. I'm just going to write it in Desmos. Okay, you get the idea. All right, so here, f of x is equal to -7 over 81 multiplied by bracket x minus 9 end bracket squared plus 15. All right, let's maximize. Oh, it's so glorious. Look at how it models the flight of that basketball. You might say, well, it didn't model it very well, Mr. Jennings. Yeah, I chose convenient points that maybe don't exactly show the trajectory of this basketball, but it's pretty darn close. And according to my model, this is going to hit the front of the rim and bounce out. Or maybe it's going to sound like a swish as it goes underneath the net and hits the netting. Okay. So these are some examples of how you can use translations of functions, particularly when you know the vertex or when you get to choose where you put the vertex, and how you can find the equations of different things in the world, and how you can describe varieties of quadratic functions as transformations of functions. Thanks very much for showing up for your learning today, and I wish you all the best. Bye for now.